Failure in composite materials is particularly challenging. This is due to two factors. The first is the breadth of different failure modes that composites exhibit. The second is the very small scale at which they occur when compared to the scale of typical composite structures. The implication in terms of numerical modeling is that we need to somehow represent and predict failure events that occur at a scale that we typically cannot afford to represent explicitly. We have developed physically based failure models for different failure modes in composites, namely matrix cracking, fiber kinking, and fiber tensile failure. One of the challenges in validating failure models is that while they may work well for the cases they were developed for, that is, materials and loading scenarios, it is considerably more difficult for them to be robust and to give accurate predictions for a breadth of generic situations. For this reason, the scientific community organized benchmark failure exercises whereby selected researchers were asked to provide blind predictions for a comprehensive range of failure scenarios for which they have experimental results. The fact that the predictions are blind and that the range of scenarios analyzed is broad are key to providing a meaningful validation against experimental results and comparison between the theories. We used our failure models in the second worldwide failure exercise, which focused on generic three-dimensional loading cases, and they were ranked first in both the quantitative and the qualitative rankings. Matrix cracking is a typical failure mode in fibre-reinforced composites, and it does not always lead to ultimate failure of composite structures. To understand the effect of matrix cracks in a structure, it is important to determine not only when in the loading history they occur, but also what orientation these cracks have. Our main contribution in this field have been to modify and extend the NASA Langley Research Center matrix failure criterion to 3 dimensions and to incorporate the effect of nonlinear constitutive response in the in-plane in-situ strength effect. Fiber kinking is a failure mode characteristic of longitudinal compression, whereby tiny matrix cracks lead to a loss of support for the fibers. This leads to a localized nonlinear deformation of the fibers, eventually involving buckling. Our main contributions in this field have been to modify and extend the NASA Langley Research Center fiber kinking failure criterion to 3 dimensions, to incorporate the effect of nonlinear constitutive response in the fiber kinking failure mode, to obtain original experimental information on the sequence of failure events leading to fiber kinking, to provide detailed analytical physically based models for the formation of kink bands, to obtain experimental evidence of a separate physical process, shear failure of the fibers, which then leads to the formation of kink bands, and finally to propose shear failure of the fibers during longitudinal compression as a possible explanation for certain characteristics of experimentally obtained failure envelopes. The physical processes that lead to the fiber tensile failure mode in laminated composites are perhaps the most complex. While failure of individual fibers does not imply ultimate failure of the structure, individual fiber breaks accumulate in small clusters, and when these clusters reach a critical size, ultimate failure does occur and is typically catastrophic. Our main contribution in this field has been to develop the first analytical hierarchical model for the fiber tensile failure mode. This model idealizes the composite in a hierarchical way, bundles of fibers composed of subbundles which in turn are composed of subbundles. Starting with the stochastic strength distribution for each fiber and the load transfer mechanism between the fibers and bundles, the model predicts recursively the strength distribution for larger and larger bundles of fibers. Laminated composites can fail when the individual lamina, that is the plies, debond from each other. This is known as delamination. Predicting the growth of the laminations has received considerable attention in the literature. Our main contributions in this field have been to incorporate nonlinear geometric behavior into an existing finite element model, to implement one of the first cohesive elements in an explicit finite element code, to investigate the effect of discontinuities in the cohesive law on stability, and to investigate the interaction between delamination and matrix cracking. In many practical applications, composite structures are applied in environments with considerable superposed hydrostatic pressure. Aircraft fuselage and pressure vessels are trivial examples, but complex geometries can themselves induce a triaxial stress state with non-negligible hydrostatic component. Our main contribution in this field has been to develop a computational model which includes the effect of hydrostatic pressure in the constitutive response. While most of the failure models in the literature are deterministic, the uncertainty associated with material properties as well as loading conditions typically lead in experiments to a stochastic response. Our main contributions in stochastic failure models have been to use Monte Carlo simulations to predict stochastic failure envelopes, to apportion the variability verified experimentally to corresponding material properties and loading conditions, and as I mentioned before, to develop an analytical stochastic strength model for the fiber tensile failure mode. In woven composites, the weave structure leads to a combination of failure modes taking place and evolving before failure of entire toes and structure occur. We have used our experience with failure models for unidirectional plies to analyze woven composites. Our main contributions in this field have been to obtain original experimental information on the sequence of failure events leading to compressive failure of woven composites, to develop an analytical model for failure of 2x2 twill woven composites under compression, to develop periodic boundary conditions which exploit symmetries in the weave, hence permitting computationally more efficient numerical models for woven composites, and finally to obtain numerically failure envelopes for failure of woven composites, both deterministic and stochastic, with the latter being obtained using Monte Carlo simulations.